Good morning, good afternoon. Welcome to IPDiA's webcast on our ultra broadband products. My name is Ijaz Hussain, and I will lead you through the discussion today in conjunction with Olivier Gaboriau, who is the PLM for this product line. Just a bit of housekeeping while everyone logs on. From an agenda point of view, the discussion will be about 30 minutes long. We'll talk about where, why, and how IPDiA's technology brings high added value, particularly in terms of unique broadband performance from 16 kHz to 60 GHz, with excellent reliability and stability. We'll also have a discussion on maximizing performance while minimizing real estate. We'll also give you an overview of IPDiA's ultra broadband product line, and we will suggest new and innovative packaging solutions with passives that are in very close proximity with active elements in order to eliminate parasitics. And we'll finish up with a 15-minute Q&A as mentioned by Leticia. IPDiA is an independent European high-tech company which was founded in 2009. We are located in France, a couple of hours west of Paris, where we have our own 19-hectare campus, which includes our management team, R&D, and production staff, as well as our own 6-inch wafer fab with Class 1 10,000 square meter clean room. Our fab is dedicated to the manufacture of cutting-edge 3D integrated passive devices on silicon. We're heavily focused on R&D, and to that end, we reinvest 25% of our revenues back into R&D. IPDiA has shown very strong engagement in the areas of medical implantable devices, semiconductors, high rail and RF power markets, as well as the optical market, which is the focus of this webcast. This slide shows our value proposition in the ultra broadband space. So what does IPDiA do? IPDiA empowers perform miniaturization, which is the process of miniaturizing and optimizing performance of electronic boards, components, or even subcomponents and modules. IPDiA manufactures ultra-miniaturized silicon passive components with high performance features, and by the way, everything we do is in silicon. Due to our patented processes of trench capacitors, we are able to integrate densities of up to 550 nanofarads per millimeter squared, which is the world record for capacitance density in silicon. We are also able to integrate the functionality of tens or even hundreds of passive components, resistors, inductors, capacitors, onto a single piece of silicon. And of course, we can take advantage of this technology to allow for silicon interposers that can effectively be used as a redistribution network on which you can flip chip your active die, and by the way, that would lead you towards the path of denser electronics in smaller modules such as QSFP 28 and SFP+. We'll talk a little bit more about the integrated passive solutions later on in the presentation. Silicon has some inherent and intrinsic benefits in the ultra broadband space. Our patented deep trench side cap technology combined with MOSCAPs provides for unprecedented levels of RF electrical performance. We have been able to take full advantage of the elementary cells and have been able to minimize the parasitic elements such as ESL and ESR in order to obtain excellent performance in the ultra broadband and RF power spaces. For example, the 0402 100 nanofarad UBSC capacitor is made up of 270 elementary cells of 370 picofarad, each distributed across the chip, combined with a 100 picofarad planar capacitor in parallel to maintain a flat broadband frequency response. This comes in with a best-in-class ESL of 100 picohenry and an ESR of 400 milliohm. As network infrastructure and indeed new iterations of pluggable modules get denser, there will be greater demands for bandwidth. Thus, there becomes a greater need for IPDiA to 1. help recoup real estate in the X, Y, and Z direction, and 2. Maintain signal integrity, especially in the 100G and beyond space. Typical applications where we play in discrete as well as custom applications are in the areas of laser drivers, laser modulators, transimpedance amplifiers, clock data recovery chips, the TOSAs, the ROSAs, the OSAs, on the main board as well as around the processor. As a side note, we also play in the test equipment space. Our ultra broadband sidecaps are suitable for DC blocking, feedback, coupling, bypassing, and also for DC decoupling applications in all optical broadband communication systems as well as high-speed data systems or products. Moreover, these UBB capacitors can support phase-sensitive broadband applications where a low group delay variation is a key factor. This technology provides industry-leading performance, particularly in terms of capacitor stability over the full operating DC voltage and temperature ranges. In addition, intrinsic properties to the silicon lead to a low dielectric absorption and close to zero piezoelectric effect, thereby eliminating memory effect. This slide shows the evolution of sizes and form factors in the 100G realm. Note that each size increment reduces the overall volume of the module by about 50% and also reduces power dissipation while maintaining optical eye performance and signal integrity. IPDiA's disruptive technology not only enables this level of miniaturization, it also helps to contribute to the reduction in power budget and also contributes to the maintaining of the all-important signal integrity and the optical eye. So this slide shows our standard ultra broadband product offering. We have 3 families of product. The first is the ULSC/UBSC surface mount capacitors. The ULSC are the ultra large band silicon capacitors, and they go up to 20 gigahertz. The UBSC are the ultra broadband silicon capacitors, which are guaranteed up to 60 plus gigahertz. The next family that we have is the ULEC and UBEC family of wire bond surface mount capacitors. The ultra large band wire bond and embedded silicon capacitor is guaranteed up to 20 gigahertz, whereas the ultra broadband wire bond and embedded silicon capacitor is guaranteed up to 60 plus gigahertz. On the vertical side, we have a UWSC series of capacitor, and that is guaranteed up to 26 gigahertz. From a platform perspective and to get an idea of where the products fit, the 20 gigahertz ULSC series of product mates well with any by 10 gig module applications. So the 10 by 10G as well as the 4 by 10G are ideal candidates for the ULSC series of product. As we get deeper into integration, the 60 gig UBSC pairs very well with by 25G module applications. So the 4 by 25G 100G module and the 16 by 25G 400G modules, as well as the 8 by 50G 400G modules, which are currently in development, are ideal candidates for the UBSC capacitors. Beyond that, our next generation of products will be guaranteed to be 100 gigahertz plus, and will be targeting the by 100G module space. This slide is from the Ethernet Alliance that shows that 50 gigabit per second modules will be here in 2018 to 2020. 200 gigabit per second modules will be here in the same timeline, and 400G modules will be here in mass production in 2017. IPDIA is well positioned to support any requirements for these data rates which are in development today. Let's move now to the electrical performances. We will talk about signal integrity, frequency behavior, group delay variation, linearity, and dielectric absorption. In this slide, we will address signal integrity. Jitter, being a significant contributor to signal integrity, is perhaps one of the most important topics in high-speed digital data signals. It is defined as edge placement variations from cycle to cycle. Some important causes of jitter are noise, crosstalk, and timing instability. This can affect timing accuracy and synchronization throughout an entire digital system. Since jitter is a function of the dielectric absorption, and the dielectric absorption in class 1 and class 2 dielectrics is on the order of 12 times the magnitude of that of silicon, then we can say that not only do IPDIA silicon capacitors not induce jitter, but by swapping out your NPO or X7R for silicon capacitors, you can actually reduce the amount of overall system jitter. Additionally, the dielectric stack is deposited using a high temperature curing process of 900 degrees C, which leads to excellent uniformity and stability of the capacitance value with memory effect close to 0. Now, looking at the S-parameter curves for the UBSC 0402 100 nanofarad silicon capacitor, you can see that we have less than 0.4 dB of insertion losses up to 40 gigahertz and 0.9 dB of insertion loss up to 67 gigahertz. Insertion losses are below 1 dB across the range, and we do not see any parasitic resonances across the range either. Return losses S11 are below minus 16 dB. This is a very competitive performance. Bear in mind that these are at nominal conditions. Our silicon caps have great stability, so you can expect that the performance will be stable across temperature and voltage variations, which is not the case with MLCCs, as will be demonstrated in the following slides. From a group delay standpoint, the 0402 MLCC component, for example, uses its 500 micron height to stack multiple electrode layers in order to reach the capacitance targeted over frequency. The inherent structure of the MLCC leads to multiple signal pathways with different parasitics, which leads to two different issues. One is multiple resonant frequencies, and the other being large group delay variations. Intrinsic to the 3D silicon structure, the IPDIA capacitor stands in at only 50 micron versus 500 micron for the same targeted capacitance over a broader frequency range. This leads to major differences in the equivalent electrical models. The bottom right representation shows that the mechanical structure of the MLCC capacitor induces significantly more complex parasitics than the single-layer silicon capacitor shown on the bottom left. Architectural comparisons between the MLCC on the left and the equivalent silicon capacitor on the right shows that a large amount of parasitics are introduced in the MLCC. Additionally, the MLCC equivalent model exhibits multiple inherent resonant frequencies. In this case, we see a major difference in group delay behaviors. The MLCC capacitor structure is inducing a large group delay variation of about 40 picoseconds. This value has to be compared relatively to a 25 gigabit per second QPSK modulation scheme where the unitary bit pulse is changing up to every 40 picoseconds also. Compared to the MLCC, there is minimal group delay variation with the silicon solution. Thus, this technology is recommended for phase-sensitive applications. Now, in reflection mode, looking at the impedance versus frequency plot of a competitor versus IPDIA, several advantages of silicon capacitors become very apparent. For illustrative purposes, we are using a vertical cap 0303 10 nanofarad with a breakdown voltage of 50 volts. The competitor's ceramic cap is also an 0303 10 nanofarad. At self-resonant frequency, the impedance is equal to the ESR. The slope of the impedance when it starts increasing is related to the ESL. So because we have a lower ESL, which is 30 times smaller, as well as an ultra-low ESR, the slope of the impedance increase in our case is lower than that of the competitor. And our capacitor, being a combination of two different capacitor structures, allows us to minimize impedance over the frequency range. We can see that the ceramic cap has a self-resonant frequency of about 100 megahertz with an ESR of about 100 milliohm and an ESL of about 350 picohenry, compared with the self-resonant frequency for the silicon cap at about 425 megahertz and an ESR of about 14 milliohm and an ESL of 6 picohenry. Bear in mind that this is based on standard IPDIA components. Please note that we can customize our components and optimize for the targeted capacitance, parasitics, as well as operating frequency. Looking at the competitive overview of IPDiA's ultra broadband series of capacitors now in transmission mode versus ceramic X7R versus X7S type capacitors, we can see several important distinctions. IPDIA is 80% thinner than X7S ceramic capacitors for the same capacitance. IPDIA has a tighter temperature coefficient of plus minus 0.5%. Versus up to 22% for the competition. IPDIA has a larger temperature range. We guarantee operation of up to 150 degrees C, whereas competition is at 125. On this point, if a larger temperature spectrum is required, that is something that we are very open to discussing. We can easily show stability of our capacitors to greater than 200 degrees C. IPDIA has a lower capacitance tolerance at plus or minus 15%, where X7R capacitors are at plus or minus 20%. IPDIA has a frequency range of up to 67 gigahertz, whereas competition only specs to 40 gigahertz. IPDIA has an excellent return loss of minus 15 dB, where the competition is at minus 10 dB. And IPDIA has an excellent insertion loss versus the competition, as we saw earlier, less than 1 dB at 67 gigahertz. And IPDIA has a better group delay of about 5 picoseconds, whereas the competition is around 40 picoseconds based on an MLCC. Another of IPDiA's key value propositions is stability. In this section, we will discuss reliability as well as stability over temperature, voltage, and time as compared to other dielectrics. From a reliability standpoint, we can show that based on fit rates and on a projected failure rate in 10 years at nominal operating conditions, i.e. 85 degrees C and 50% of the rated voltage on 1 million units, you could expect to see about 200 failures with an X7R and close to 500 failures with a tantalum-based device. With silicon, we only see 2 failures out of 1 million units over 10 years of operation. That is 100 times better reliability than X7R and 250 times better reliability than tantalum. So if we extrapolate the findings from the previous slide to a real-world example of a data center in which there are 8,000 servers with 4 modules per server, that adds up to 32,000 modules. With a per module capacitor count of about 100 units, that adds up to 3.2 million capacitors within that data center. If the capacitors are MLCCs, based on published fit rates, we can expect to see 245 failures in the first year alone and a cumulative of 2,400 failures in 10 years. With IPDiA's UBSC silicon capacitors, we see 0 failures in that same 10 years. Now, if we increase the number of servers from 8,000 to 50,000, we finally end up seeing a single failure on an IPDiA silicon capacitor, and that's after 10 years. In the same period of time, and over the same number of servers, you could expect to see many thousands of failures within those 10 years with MLCCs. Apart from reliability, a key value proposition with silicon is stability. When designing with ceramic capacitors, you need to oversize the capacitors since you can expect losses based on temperature, DC bias, AC voltage characteristics, as well as aging. IPDiA silicon capacitors are agnostic to these influences, so as long as you know the effective capacitance that you need, you can go ahead and design based on that capacitance without having to take into account influences based on the dielectric. For example, from the first graph on the top left, you can view degradation based on temperature on all of the ceramic-based parts. Some of the degradation, in fact, is very prominent, whereas you can see that IPDiA caps are stable up to 200 degrees C and beyond. Same discussion for the DC bias, AC voltage characteristics, as well as the aging. If you multiply these degrading effects, you can easily see up to 70% degradation. So when using ceramics, oversizing is an absolute must. Whereas with IPDiA silicon capacitors, due to the intrinsic properties of the silicon, you can get away with using a much smaller part with the capacitance that you actually need without having to be concerned about oversizing. Conversely, you can get a much larger amount of capacitance in the same footprint as an MLCC. Please note that with IPDiA capacitors, there is no piezoelectric effect. Now let's talk about another of our key value propositions, which is miniaturization as well as capacitance range. We have been speaking a great deal about our standard capacitors as well as our customized capacitors. This slide shows a breakdown of our capabilities to integrate capacitance into a specific package size. The arrows show the products that we currently have that are on the shelf and are available for immediate sampling. In addition, the slider shows what our capabilities are, i.e. capacitance versus capacitor type versus form factor versus breakdown voltage. For example, on the UBSC horizontal type silicon cap 0201, we currently have a 10 nanofarad part available in full production. However, we are able to develop and manufacture any value of capacitor between 1 nanofarad and 22 nanofarad with a 30 volt breakdown voltage, as well as a 47 nanofarad with an 11 volt breakdown voltage in the same footprint. Similarly, with the 0202 WBSC vertical cap, we currently have a 10 nanofarad part available in full production. However, we could also develop a 10 picofarad with 450 volt breakdown voltage all the way up to a 22 nanofarad with a 11 volt breakdown voltage in the same 0202 vertical format. Let's concentrate a bit now on size reduction and miniaturization. As the world moves towards smaller and smaller form factors, real estate in the X, Y, and Z directions becomes more and more precious. By virtue of the fact that SiCaps are made of silicon, and since we can pack a much larger amount of capacitance into a smaller area, thereby saving real estate, IPDIA can help empower you to make the leap to the next generation of miniaturization. Not only that, we can help you recoup real estate that can now be used to add feature set. In this example, we show that from a thickness standpoint, we have a standard thickness of 400 micron, a low profile thickness of 100 micron, and we have 30 micron available on request, all with no loss of capacitance. Compared to the same value of capacitance of a tantalum cap, we are 20 times thinner. Now, from an XY perspective, we can also show that for a COG type 1 class capacitor, the maximum capacitance value in an 0402 package is 10 nanofarads. The IPDIA 0402 silicon capacitor is rated at 100 nanofarads. In other words, it would take 10 COG capacitors to be equivalent to a single IPDIA silicon capacitor. However, taking into account the placement courtyard, we can show that a single silicon 0402 100 nanofarad capacitor can introduce an actual real estate reduction versus COG of 20 times. The same situation applies with class 2 dielectrics. However, with X7R, the minimum thickness is 400 micron, whereas IPDIA standard low profile thickness is 100 micron. We also offer packaging and assembly options where we can act as an interposer and your chip can be mounted onto the substrate. We also offer flip chip capabilities. Parts can be embedded and also assembled in JEDEC packages. We also offer wafer finishing services from metallization to bumping to copper pillars to back grinding. With respect to packing options, we can ship individual wafers, sawn wafers on tape, sawn wafers on frame or on ring. We can send a singulated die in the tape and reel format, as well as in waffle pack. We can also package into standard JEDEC packages. As well, we can ship engineering samples in gel packs. A quick word on quality certifications. IPDIA has a full suite of quality certifications that conform to the electronics industry, from ISO 9001 to ISO 14001. We are also TS 16949 automotive certified. We are also RoHS and WE compliant. The jewel in the crown of quality certifications is the ISO medical certification, which allows us to engage in medical implantable and life-critical programs. Of course, this speaks to the quality and reliability of IPDIA processes. So, in summary, the key takeaways and value propositions from IPDiA's ultra broadband silicon capacitor technology are the following. IPDiA's ultra broadband silicon capacitors are designed to improve signal integrity and optimize the overall broadband optical system performance, and to support upcoming generations of module miniaturization and integration. From a supply filtering DC decoupling and a bypass grounding standpoint, the key takeaways are low ESR, low ESL, high self-resonant frequency, and of course we're very stable over temperature and voltage. From a signal transmission, AC coupling, DC blocking, and feedback standpoint, the key takeaways are low insertion loss, stable phase, low group delay variation, high linearity, no piezoelectric effect, low dielectric absorption, no parasitic resonances, and of course we are very stable versus temperature and DC bias. Very important to note that we are much more reliable than MLCCs, and of course, IPDIA does empower miniaturization from a custom IPD standpoint to capacitor arrays to RC networks. So thank you for your time and your attention, and now we will open the lines up for questions.